we're still in the idea of geochronology. How do you put an age on a rock in an absolute way? In our textbook, this topic of geologic time is covered in chapter 7. And so last time I introduced to you what is an isotope. We did radioactive decay. Of course, you can do Wikipedia on any of these and learn so much more detail. And we also introduced half-life. Now, if we put all of these together, I guess what we could say is these are all the variables that are needed in order to make a calculation of how old a crystal or a rock is. So today what I want to do is give you the master equation for geochronology. The master equation for geochron. There's small variations on this, but basically if you understand this equation, you can apply it to any of the almost 30 different radioactive systems out there that geologists are using to calculate time. And so the equation is D equals D sub 0. So this is daughter equals daughter original plus parent, it's P, times E to the lambda T, that's a lambda here, okay, lambda T minus 1. That's our equation. Let's define the variables. D equals the amount of daughter now you can measure in a rock. D sub 0 is the amount of daughter initially, when a crystal first formed. That ends up being a bit of a problem. P equals the parent now. Oftentimes in textbooks this is given the symbol capital N, but I'm changing it to P because parent starts with P. All right, what else do we have in this equation? We have lambda, right? You remember what lambda was? Lambda was it's called a decay constant. It's related to half-life. Okay, so I'm going to just put this is related to half-life. And then our final variable in here is T, which equals time or age, and this is what we solve for. So this equation is commonly rearranged to solve for T. So what we need to do in order to apply this equation is we just need to know these variables. And if we know those variables, it's a simple algebraic equation. So what I want to show you now is let's call this now the approach. How do we actually know these variables or make assumptions that allow us to deal with them appropriately? This is going to be a short list. The first thing we're going to do is that we can actually measure two of the variables with instruments in our research labs. And what we can do is we can measure both D, the daughter now, and parent now on a machine called a mass spectrometer. Mass spectrometer. What a mass spectrometer does is it measures the mass of something. Okay, so spectrometer means like instrument, and then mass is what it's measuring. And so let's see, so N and D are counted. Okay, I guess in this lecture we're using P here. And this is like the surface of a crystal that has been ablated by a laser, and the laser vaporizes this mineral and it shoots through the instrument. Let me see here if I can do this. So what it does is the laser hits your sample and it turns it into dust. The dust then shoots through the instrument into this magnet. This right here is a magnet. And the magnet separates things out by mass. So things that are heavy go here and things that are light get bent by the magnet more. And so you basically count ding, ding, ding each time heavy mass or light mass or intermediate mass passes through the magnet. So that's the process of a mass spectrometer. 100 years ago, these things were high technology, maybe not even invented yet. Nowadays, they're a little more routine. My geology department has about a dozen of them in the building. So lambda, how do we get that? Well, this is a constant, and it's like one of the laws of nature. It's measured by physicists, and we just take it from them. Number 3 in our list of concepts or assumptions or approaches is we're going to say it's a closed system. Imagine a submarine underwater. You want it to be a closed system for water, a closed system for oxygen. Things don't leak in and things don't leak out. The same is true for a mineral when we're doing geochronology. We're going to make an assumption that no parent or daughter leak in or out. And this would be a process called diffusion that could be impacting. Okay? Sometimes it's safe to make this assumption and sometimes not. It's some of the higher level science associated with geochronology. And then finally, D sub 0. How can we go backwards in time and know what the amount of daughter is? This is also something that is sometimes safe and sometimes not. Usually the system allows for, usually is 0. Usually geochronology is performed on a system where when we go back to the master equation, we can actually remove D sub 0 as a variable. All right, so now let me go through an example of this. So we're going to do one example system. And the example system I want to walk you through is uranium-lead geochronology. This is commonly done on zircon, but it can also be done on other minerals as well. Here's an example of some zircon crystals, where here's like a hand sample of zircon, this beautiful red tetragonal crystal that has a chemical formula of ZrSiO4. There is no uranium or lead in this chemical formula, but the chemical formula represents its perfect state. But what can happen is that there can be some uranium 4+ that substitutes for zirconium 4+ in the crystal lattice. And this is what's going to allow zircon as a mineral, in fact we should write down the word, let's write the word zircon, as a mineral to do geochronology. The reason why uranium can substitute for zirconium is it has the same charge at 4+, and then it also has the same or very similar ionic radius. So you can imagine at the lattice level, the ball and stick model, you can have some uranium for that zirconium. Now these two pictures over here are microscope images of zircons, very tiny, like 100 microns across. And what's interesting, you can see these various tree rings. And so zircon is growing with time like a tree, and it's incorporating uranium at different amounts as it grows. And we're going to measure that with a mass spectrometer. So the next most interesting thing, I guess, that we need to say here is that when uranium 4+ substitutes for zirconium 4+, it actually does it as two different isotopes. It substitutes some as uranium-235, and some of it comes in as uranium-238. Two different isotopes. And then the decay scheme is uranium to lead. So uranium-235 is going to decay to lead. Uranium-238 is also going to decay to lead. So let's say this. We have two isotopes of uranium. Now here's an interesting thing. If we're decaying to lead, how many isotopes of lead do we have? So in nature, lead has 5 different, well actually, let's say this. Lead has like 25 different isotopes, but 5 of them are common. And so there is lead-204, there is lead-206, there is lead-207, there is lead-208, 208, and there's also lead-210. And they occur in different abundances. So lead-208, this is about 1% of all lead in nature. Lead-208 is about 50% of all lead in nature. This 206 is about 25%. 207 is about 25%. And the way each of these form, this is like 0%, and it forms by cosmic processes in outer space, so it's not one we need to worry about. Lead-204 is stable, but it's a 2+ charge, and it's also 130 picometers in, what do we say, in ionic radius. And so it just cannot fit in the lattice of zircon. So this one also doesn't matter. Lead-206 forms from the decay of uranium-238. So that one matters. And the half-life for this is 4.5 billion years. Lead-207 forms from the decay of 235, uranium-235, and it has a half-life of 0.7 billion years. And then lead-208, which actually makes up the majority of lead out there, it actually can either be stable or form from radioactive decay of thorium-232. 232 thorium or stable. So that presents a problem, except for we have a mass spectrometer that can actually be tuned to a specific mass. And so we can actually get rid of this and not measure it in a mass spectrometer and tune the instrument only for lead-206 and lead-207. In fact, that's important enough that we're gonna write it down here. Tune mass spec to only count 238U plus 206 PB, and we're going to tune it to 235 uranium and 207 PB. And then we can calculate an age from one decay scheme that has a half-life. We can calculate another age from another decay scheme, and what's really cool about this is you have two different decay schemes, they better match. And we can ask ourselves, do they match? And if you get an age that from one that matches the age from the other, you can be pretty dang confident that your age is correct. And the way that we do this in geology, it's a diagram called the Concordia diagram, which is beyond the level of this class, but we find the ratio of 206 lead to 238 uranium, and we plot it against 207 lead over 235 uranium, and perfectly correct answers will fall along a line which is concordant, hence the name Concordia diagram. And so if a rock is 1 billion years, it'll plot there. If it's 2 billion, if it's 3 billion, or 4 billion. So if we had an example and it plotted right on the line right there, we would say we have a concordant answer at 1.2 billion years. We've just dated a rock. Now there's so many other systems out there to date rocks that have been developed. I'm not going to talk about really any of them right now. I do want to just briefly, before we're done, talk about carbon-14. It's the most famous, and it has a half-life of 5,730 years. And the way it works, carbon-14, if we put some half-lives in, so T to the 1/2 equals 5,730 years. It's a very short amount of time, and that's one of the keys to this, is that it has a short half-life. Short half-life. So one of the problems with it is it has a very short half-life. It can only date things up to about 60,000 years, 60 KY limit. And the reason why is if you start with 100, after one half-life, you're down to 50, right? After another half-life, you're down to 25. So what would that be? That's 5,730 times 2. That's like 11,400 years. After 3 half-lives, you're down to 12% of the original carbon, and then you're at like 16,000 years. And by the time you're at 60,000 years, there's just no carbon-14 left to do measurements. The other thing about it is that the C14 is from photosynthesis, or from like a animal, like a deer, eating plants. And so when something dies, the incorporation of C14 stops. So let's say C14 is from ingestion of plants. The clock starts at death. And so here's what I want you to think about with this. A rock is never alive, unless it was coal or petroleum, right? But generally when we're measuring things, they're inorganic. They don't have C14 ingested. So carbon half-life is more for archaeology and the study of like ancient human civilizations or plants than it is for actual geology and rocks.